So far, we have learned that how to use Hadamard gate on a single qubit. Hadamard gate is a single qubit gate, so it can be easily applied to transform a single qubit. However, we can extend Hadamard gate for multiple qubits using tensor product and can apply it on multiple qubits. And this is the subject of this video, that we will learn how to apply Hadamard gate on multiple qubits. So let's say we have given Hadamard gate and we have to apply the Hadamard gate on a 2-qubit register. In that case, a Hadamard gate will be written as Hadamard gate tensor product 2. This tensor product 2 implies that if we have to extend Hadamard gate on a 2 qubits, this Hadamard gate is not a single qubit gate, but it's a 2-qubit gate. And afterwards, we will have a register here which will be a 2-qubit register. For the sake of example, let's say our register contains ket 00. So we have to basically find out that what is the outcome of this expression is. So there are two methods to solve this expression. One method is using matrix. So one method is using matrices. The second method is by using the single qubit Hadamard gate. So second method is using the fact that Hadamard gate on ket 0 is equals to ket 0 plus ket 1 divided by square root of 2, and Hadamard gate on ket 1 is equals to ket 0 minus ket 1 divided by square root of 2. The second method employs this concept, whereas the first method use matrices. In practice, we use this method more often because it takes much less time, and this method works when we have to use Hadamard gate on more than 2 qubits also. But this method is good to understand the basic concept and to develop intuition. So let's start with the matrices method, which is not commonly used, but it is good to develop intuition. So what we are given is that we have to apply Hadamard gate tensor product 2 on a 2 qubit register which has ket 00 in it. So this implies that I have to tensor product Hadamard gate with itself. So this expression implies that I have to do this operation, Hadamard gate tensor product with Hadamard gate. So we know what is Hadamard gate is. So we know Hadamard gate in the matrix form is that we have 1 over square root of 2, and then we have 1, 1, 1, minus 1. So now what will be Hadamard gate tensor product with itself? So when we say tensor product with itself, then it implies that this number multiplied by this whole matrix, this number multiplied by this whole matrix, this number multiplied by this whole matrix, and this number multiplied by this whole matrix. So what we will get at the end is that when we multiply 1 with this whole matrix, we will have here 1, 1, 1, minus 1. So this here is this whole matrix. And these normalization constraints will also multiply with each other. So we will have here 1 over 2. So this, I'm just writing here dots for the sake of understanding that this is this whole matrix multiplied by 1. Similarly, 1 multiplied by this whole matrix, we will have here 1, 1, 1, minus 1. Similarly, this 1 multiplied by this whole matrix, we will have here 1, 1, 1, minus 1. And finally, we have minus 1 multiplied by this whole matrix. So the last entry will have all the sign reversed. So we will have here minus 1, minus 1, minus 1, and this minus 1 will become plus 1. So that's our Hadamard, this is our Hadamard gate tensor product with itself. This is our this expression. Similarly, we can do Hadamard gate tensor product 3 times. We have to basically once again tensor product this matrix with another Hadamard gate, but that's we are not doing in this video. So now I have to find result of this thing. So I have found what this is, which is this. Now ket 00 is a 4 elements vector, is a 4-dimensional vector whose first entry has 1 and rest of the entries has 0 in it. So we will have here 1, 0, 0, 0. Now we multiply this matrix with this vector and we will have our final result. So in this case our final result will be the first column. So our final result is going to be 1 over 2, 1, 1, 1, 1. So that's it with our matrices method. But matrices method becomes very difficult when we have more than 2 qubits register. We have 10 qubit register. It's very difficult to write a huge matrix for 10 qubit register. So we usually use this method. So now let's start with the second method. So our second method is extremely simple. So in our second method we have to calculate Hadamard gate tensor product 2 with ket 0, 0. So first of all we can write this ket 0, 0 as ket 0 times ket 0. So we can write it like this. Hadamard gate tensor product 2, and we can write here maybe ket 0 times ket 0, and then we can basically simplify it like this: ket Hadamard gate to ket 0 and Hadamard gate to ket 0. So this is our second method. We are applying Hadamard gate on each individual qubit of the register. So we know that Hadamard gate ket 0 is this thing. So our result going to be 0 plus ket 1 divided by square root of 2. We know Hadamard gate ket 0 is once again this thing. Our result going to be ket 0 plus ket 1 divided by square root of 2. And now we have to simplify this. Our result going to be ket 0 times ket 0 will be ket 0, 0. So we can also write it ket 0 and ket 0, but usually we write at ket 0, 0. And ket 0 times ket 1 is going to be ket 0, 1. And this will going to be ket 1, 0. And the final terms is going to be ket 1, 1 divided by 2. So that's our final result. And this result and this vector is both are the same because this vector is equivalent to this. In this we are saying that we're going to have 1 at the first position, we're going to have 1 at the second position, we're going to have 1 at the third position, 1 at the 0th position, first position, third position, and the fourth position. And here we have 1 on all those positions. And we are saying that our normalization constraint will be 1 over 2. And we have our normalization constraint of 1 over 2. So using the both method we have the same result, but this method was much faster and less prone to error. So now one very important thing is left, that how to express Hadamard gate in general terms when we have n qubit, how to apply Hadamard gate on n qubit. So let's start that.